The problem's a little more manageable when we set today equal to 0. Notice again that we have the summation that basically says that we're adding up each of the quantities. You can also see that when time is equal to 0, then that goes to 0 and this whole thing collapses, which makes sense because the present value of $1 today is $1. There's no discounting. When the time is equal to 1, then that quantity that we receive at time period 1 is going to be discounted back 1 period. If it's 2, the quantity in time period 2 is discounted 2 periods, just exactly what we did on the screen before in trying to calculate the present value of a series of payments. So that formula is just a way of summarizing what we did. Again, as we said before, if you have an annuity that's uniform or the same, we can rewrite that as A instead of having to subscript the amount. Notice that this is a uniform annuity, so we can try and calculate or present a present value uniform series of payments or uniform annuity. Again, we start with this idea that we're going to take this uniform annuity and we're going to discount it back appropriately to each sum of money to get the present value. Using rules of series, we can come up with a factor that gets rid of that summation. So it makes it so we don't have to sum up each amount. Saves us a lot of time. And again, we're going to rewrite that. We're going to take what's in this 1 minus 1 plus r to the minus n over r, and we're going to just call it the USPV, the Uniform Series Present Value factor at some rate r and some level n. Again, this is at the end of the conversion periods. If it was the beginning of conversion periods, we'd have to calculate another factor. So in this particular problem, you can see that there's a series of payments and it's uniform. And in this particular case, we want to know the present value. So we want the present value on the left-hand side of the equation. So we're going to use the present value of a uniform annuity formula. And that's the kind of the logic to determine whether you use the present value or the future value uniform annuity. What are you looking for? You're looking for the present value, you're looking for the future value. We can again use our calculator. We can see that there are 4 periods. So we're going to put 4 into our calculator. The interest rate is 10%. That was a given, so it's 10% I. The payment, you can see, is 100. So we put 100 payment. Now, in this particular case, why do we zero out the future value when there's clearly a future value in this timeline? Okay, these 4 payments are already accounted for here in the payment, right? So if you were to put another one here, you're double accounting. So that's the solution. We come up and get $316.99, which is what we did before. We can use Excel to calculate the present value of a uniform annuity. And what I have on the screen is the formula for doing that. Basically, it's the present value. You have the interest rate. You have the number of periods. You have the payment. And remember, we said that the future value in that case was already accounted for in the payment, so we zero it out. It's the end of period cash flows. As you can see, it gives us the same answer as when we plugged it in on our calculators because, as we expect, it's using the same formula. Okay, as promised, today we're going to now see how we can use this formula, the present value of a uniform annuity, for some applied type of work. We're going to use it in terms of capital recovery. And to define this capital recovery, basically we are going to take the formula for the present value of a uniform annuity and solve for the annuity. So we are, in this case, we're going to calculate that annuity that's equivalent to an investment or a single sum of money at the present over its maturity of n periods given a rate R. And we can use this concept for fully amortized loans. Fully amortized loans are what's typically used if you're borrowing money to buy a house or to purchase a car. We're going to call it fully amortized loan. We refer to it as capital recovery because if somebody is lending you money, they have to recover that. They need to get the principal back, plus some be compensated for it. We're also going to talk about it in terms of capital investments. particularly those of you that are in production agriculture or ag systems in those particular areas. You may have seen this before in some cases in your production classes and even some of your ag systems classes. You may do approximations. Here we're going to show how to calculate the actual capital costs, as we refer to as capital recovery. If you buy a tractor, what's the actual cost of that? What do you have to recover each year to pay you for that initial cost of that equipment? As promised, this all comes out of the formula that we have stated is the present value of a uniform annuity, where A is the uniform annuity, and we're bringing each of its components back to the present. But because it's uniform, we calculated this formula that we see in brackets that allows us then to avoid having to use the summation or treating each component separately. It's done through the formula that was calculated through the arithmetic of series. And we said that if we know the present value and we know the rate and we know the number of periods, then we have to solve for A. And of course, solving for A, we just have to divide both sides by the factor that we have in brackets. So there's nothing real sophisticated here. It's just you have one equation and you solve for one unknown. Don't fight this, because for the rest of the course we are going to be doing that. We're going to have basically 4 formulas that we're going to use, and then most of our problems are looking at the knowns and solving for the unknown. And all of them in this class are simple because we're doing it with single equation. In your mathematics courses and courses beyond, of course, you may have multiple equations with multiple unknowns. Okay, going now to the fully amortized loans to see an example of this. If you borrow $10,000 and pay it back in 10 equal annual payments, being principal and interest at 10% interest, what is your annual payment? To put this closer to home, you want to buy a $10,000 Ford Escort. Say, what would be your annual payments for this particular loan? Again, the verbiage. Strongly encourage you to learn how to take the verbiage or the wording of these problems, particularly as they get longer, can get a little bit frustrating. If you'll learn to pull out the numbers and put them in a timeline, you'll save yourself a lot of frustration. Which we do in this case is we draw our line and we see that we're going from today, the present, which we designate as 0, to the end of the 10th period. Again, remember the dots just mean repetition, or those numbers are being repeated, and we can use that to save space on the screen. We know that we are receiving $10,000, we're borrowing $10,000, so we're placing that in as a positive, and we're going to pay the bank back in a uniform amount at the end of the period for the next 10 years. Okay, if the interest rate is 10%, the unknown is that annuity, that A, that we're going to pay back every period. That's your payment. It's capital recovery because the lender paid you $10,000. Now you have to pay the bank back so that the bank can recover the capital that the bank lent you. Now if we look at this and we say, how do we solve for that? Okay, the logic here is, do we have a uniform annuity in this problem? Do we have a payment that is constant and repetitive? Do you recognize this as a uniform annuity? Do we also see that in this case we have a present value? So we have a uniform annuity and we know the present value. So which formula are you going to use? The present value of the uniform annuity, which we define, then we plug the numbers into it and then use our calculator. So we can see that there's, in this particular case, we're dealing with 10 periods. If we put 10 in, we can see that the interest rate is 10%, so we put 10I. We see that the present value in this case is $10,000, so we put $10,000 in the present value key. Now in this case again, notice that we put a 0 in the future value for the same reason we did before, is because all the future values that are indicated in this problem are already accounted for or will be accounted for in the payment. So now we compute the payment, which was our unknown, and it comes out to $1,627.45. If we were to pay off this loan, then we'd have to make the $1,627 payment per year. Now, how much of that is interest? In this case, you're making 10 payments of $1,627 over that period of time, right? So your total payments, $16,274, and $10,000 of that's principal. So we're paying how much interest? $6,274. We're making $1,627 10 times, so we're paying the bank back $16,274. We borrowed $10,000, so $6,274 is interest. I mean, hopefully that's a revelation to you. Over that 10-year period of time, you've paid over half as much in interest as you did for the original whatever you purchased. It also helps illustrate what I was saying on the sinking fund, why something that you need to consider now is to set up a sinking fund to make your payments to yourself if you're planning on purchasing a car, so that you're paying yourself the interest instead of somebody else. Now, as a digression, we can calculate this capital recovery factor as a payment using this formula. And we simply say equals payment, put in the interest rate, the number of periods, the present value, the future value, and the type is 0 because it's end of period, and it's going to give us the same answer as the calculator, again, because it's using the same formula. Now, continuing with capital recovery for capital investments. This is more in the management realm, particularly in machinery or businesses. You want to know your capital recovery or how much it's costing you. Basically, you can think of it this way. How much is the capital costing you on an annual basis? In many classes, they teach you how to do this, ignoring the time value of money, which is similar to evaluating the pizza with linear inch. It looks nice, it gives you an answer, you feel good about it, but it's not the right answer. So for those of you that are involved in production agriculture and doing enterprise budgets or evaluating machinery, this is the basic principle here, is something that you need to internalize. And we're asking it here as a simple example. If you were to buy a tractor for $30,000 and then you plan on selling it for $5,000 in 6 years, what is the annualized cost, referring to the capital recovery of that machinery, if you have opportunities to invest your money at 10% or if you're receiving interest or paying interest at 10%? This could be also if you wanted to know, if you're thinking about purchasing a car or a truck and you wanted to know your true annual or true monthly costs associated with the purchase of that depreciable asset, go through the same process. Now, to do this, we're going to first calculate the present value of the cost, okay? Because the cost, we have to recognize that we're putting out a chunk of money today, but we're going to get a chunk of money back at the end because we can sell it. It's got some salvage value or terminal value. And then second, once we know that value all in today's dollars, then we can annualize it through the planning horizon or the life of that investment. So we're going to do it in 2 steps. And recognizing now that as we get into more problems, particularly in finance, you're going to find that problems are sequential. We have to solve one piece as input into the next piece. When you get into analysis, that's what you have to do. You can't just look at it and say, oh, that's the answer, I've got it. You have to analyze it. You have to look at the pieces, and you have to calculate the one piece that fits into the next piece. And this is a simple example, but progressively, as you'll see, there's more of that sequential steps to get to the correct answer. You have to recognize when you're dealing with finance, you're dealing with time, you're dealing with risk, you have to learn to analyze and learn things sequentially. So in this particular case, we're trying to find the present value of the cost. And the $30,000 that we pay today for that tractor is already in present terms, so we don't have to do anything with that. But with the $5,000 that we get in 6 years, we have to remember that. We have to think of it in our timeline. We're getting $5,000 at the end of the 6th year, and we want to know how much it is today, and the interest rate is 10%. Then obviously, to solve for that, we would say V naught is equal to 5,000 times 1 plus 0.10, and we discount it back 6 periods. And what you see here is exactly what we're adding to the $30,000. Okay, so we're not doing anything magical here. We're just discounting that sum of money that we're going to get in 6 years, that $5,000. We're converting it, we're transforming it to present dollars. That's an equivalent amount to the $5,000 in 6 years. And you can see that when we add the two together, or when we take the negative $30,000 and then add the discounted value of the $5,000 salvage value, we have a cost in today's dollars, okay, this $27,177, meaning that the cost has been mitigated by the fact that we get some of that back. But you also have to remember, however, that $30,000 we have invested for those 6 years. We have lost the use of that money for the 6 years, so we have to account for that. So in the previous slide, we calculated the present value of its cost, or the cost of that tractor today. What we want to know is, what does that cost on an annual basis over the life of this particular tractor? Now, if we want it uniform, we're going to use this A, so we have a uniform cost, annual cost over the life. We're assuming that the interest rates are at 10%. We can see in this particular case which formula to use, again, because we can see that it's a uniform annuity. So we know we're going to use the uniform annuity factor. We're going to use the present value because a present value is given. So those are the keys that say that we're going to use the present value of the uniform annuity as opposed to the future value. Because if you tried to use the future value, what would you plug in? You would have had two unknowns. You would have had to calculate the A and the future value. And since you can't solve for two unknowns with one equation, then obviously by default you can figure out that you need to use the present value uniform annuity. All right, in this particular case then, we can see that the number of periods is 6. So 6N, the interest rate is 10, the present value in this particular case is negative 27,177.60. We zero out the future value, we calculate the payment, and it comes out to $6,240.18. Now what does that $6,240.18 mean? That's the cost of what? Basically the cost of having your money invested in that tractor and the loss of value because it's depreciating, in this particular case, $25,000, isn't it? Now if you wanted to, going back to our pizza in linear inches, we could have taken the $30,000 of its cost and subtracted out the $5,000 we get back and divided it by 6. And what would our answer be? 4,000? So if you wanted to evaluate the cost of owning that tractor, like we evaluated a pizza, we would have come up with an answer of a cost of $4,000 per year. Looked good. Made sense, didn't it? Cost you $30,000, you got $5,000 back. It means you cost you $25,000 for 6 years to own that tractor, didn't it? You had it for 6 years, divide it by 6, give you $4,000. There's your answer. But is that the correct answer? It ignores what? The time value of money, or your opportunity cost. You had that $30,000 tied up that could have been earning interest on another investment, or you were paying interest on it. So be careful in your production classes. It's very easy to do these just summing up sums of money through time. It looks good, but you can see there's a big difference between $4,000 and $6,000.